All right. So welcome to this tutorial, an introduction to Vulkan. My name is Johannes Unterguckenberger from TU Wien. Currently, I'm with Huawei, though. So in case you didn't know, Huawei is doing real-time rendering research right here in Munich. So they have a cloud rendering lab here. And yeah, research in the field of cloud rendering, real-time rendering. So if you're maybe looking for a job at some point in the future or consider them maybe, or they also offer a master thesis for students. So great options. And I would personally like to thank them for providing me enough time to prepare for this tutorial. So that was really great. Okay, so speaking of the tutorial, let's get back to it and back to TU Wien. So I'm not here alone. Doesn't work. I'm not here alone, but I'm joined by a whole bunch of people, namely Lucas here and those 4 awesome people in the back who are here to assist during this tutorial today. So it's Elias, Andreas, Victoria, and Annalena in the back additionally. And so we start off, so this is our schedule for today. We are right here now, so in the 10 minutes setup session. So then we have 20 minutes lecture, and in between these longer coding sessions where you are supposed to code, to learn the Vulkan API hands-on. And all of us are here to assist you with that so that you do not get stuck. Because it's, maybe if you're new to Vulkan, it's maybe quite a lot of code you have to write. So whenever you get stuck, just ask for help. Okay, yeah. What are we going to implement today? We're going to implement today a small model loader. In the first part, we will end up with this result, which is a nice red teapot. Then after the second part, we get a smaller orange teapot. But don't worry, we will change everything underneath it. So it's, yeah, just the result is not much different. Then things start to get more interesting. And finally, we end up with a nice model loader with shading and so on. So we are using buffers, images, and everything that Vulkan provides. And you will see how easy it goes or how much pain it will be. So with part 1, where we're going to talk about fundamental Vulkan handles, Windows system integration, and the swap chain. Okay, so fundamental Vulkan handles. There are a few that we are, or a bunch of that we will need, and we will get hold of them during this first part. So let's start with the instance. The instance represents Vulkan on your system, so to say, and it actually represents the configuration in which you are going to use or are intending to use Vulkan on your system. You can enable extensions and so on for that. So if you configure an instance and then you use that as an interface to Vulkan. So this is the first step. Let's jump right into the code, how using the Vulkan API looks like. So at the bottom, we see the call to VK create instance. Okay, this gives us back a handle to VK instance if successful. And Vulkan always assigns them through references. So this is just how the Vulkan API is structured. This is a common pattern throughout the whole API. And what's also a common pattern is such a configuration structure. So instead of having loads of parameters for the functions, you have loads of parameters in the members of the configuration struct. As a best practice, we always zero initialize it because there are pointer members in those configuration structs, and we want them to be null pointer if we're not using them. Then there's for most of the structures there is this S-type member, which you have to set to the type of the structure. So in this case, we can see the structure is called VK instance create info, and the structure type is VK structure type instance create info. So it's just, the naming scheme is just this, and you have to do this for almost every struct that you're going to use today. Then we have pointer members, like I mentioned before. So points to another configuration structure. If we're not using that, it would be good to zero initialize it. But in this case, we're using it for setting the API version that we would like to have our Vulkan instance running. So in this case, in this example, we would like to request Vulkan 1.2. Yeah, the current version of Vulkan, the most recent version is 1.3, but in this case, in this example, it's just 1.2 requested. Maybe for compatibility reasons. Okay, moving on. There are extensions. So we would like to have our Vulkan instance running with these extensions enabled. In this case, the extensions refer to surfaces, so surface support. In order to draw something onto a Windows surface, we need to enable these extensions. And you can see here, it's Windows specific, so we enable a general surface extension to Windows extension. So this is the configuration that we would require Vulkan to run in. If you don't get it, the creation will fail. Another useful thing are the layers that can be enabled. Here we are using a validation layer. We will see later an example of why we would like to use validation layers. Yeah, just for now, we enable it during instance creation. And so much for that. Move on to the next important handle, which is the Windows surface. The Windows surface is a connection to your operating system. So what we will be doing is we are using our Vulkan application, and at some point we would like, and our Vulkan application renders the result into an image. And at some point we would like to have this image that we rendered being presented on a window surface. So we hand it over to the operating system and ask the operating system to present it on a screen. And in order to do that, we need such a VK surface KHR handle. We will just need it to send over a surface to the operating system for presentation. Then moving on to the physical device. The physical device represents one device in your computer that is capable of running Vulkan. So this will be your GPU, or if some of you might have laptops that have two GPUs. So then you will get two physical devices that are capable of running Vulkan. So just as indicated before, in this case we have the situation where we have a computer with two GPUs. So in Vulkan, we can select which GPU we want to use for which tasks. So very specifically. So we can either use GPU 1 for rendering everything and for presentation, and maybe for other tasks as well, whatever our application requires. Or we could also select GPU 2 to do all the rendering and then use GPU 1 just for presentation. Or we could distribute our workload on both GPUs. So I don't know, maybe one GPU works on something that can be processed in parallel and would be possible, totally possible in Vulkan. You have to very expressively select which GPU performs which tasks in Vulkan. So how do we get hold of a physical device? In this case, it works through VK enumerate physical devices. So it's not create physical device, but it's enumerate physical devices. And here we see another common pattern of the Vulkan API, which is we need two calls to the same function sometimes. The first call of VK enumerate devices takes null pointer as a last parameter, which means it assigns the count. How many physical devices are there? And then a second call to VK enumerate physical devices, where we pass an array of sufficient size instead of null pointer to the last parameter, assigns all the handles of the physical devices. So we need two calls. First for the count, second to get all the physical devices. And then we just select the physical device by its index. In this case, we select the physical device at index 0. There are further helpful methods. So if you would like to select the physical device based on its capabilities. For example, one GPU might be capable of doing ray tracing while the other might not be. For example, if you have two GPUs in your laptop, that might be the case. So you can use those methods to query the features that a physical device supports. Okay, moving on to the queue. So we have to talk about the queue already in this first part, because it needs to be, or queues need to be created and specified during device creation. So device creation, we talked about the physical device, but there's also the logical device, which we'll talk about in a minute. The logical device is the interface, the main interface to a physical device. But before, we have to talk about queues, because we need to specify how many queues we would like to be created when we create a logical device. Okay, what is a queue? A queue is a concept of Vulkan, which takes commands which you would like to be executed on a device. The queue receives those commands and schedules them for execution on a physical device, on a GPU. So in this case, one command has been sent to the GPU and it's executed right away. We can send multiple commands to the same queue. So we just send them and send them and send them. And your GPU is a massively parallel processor. And as soon as it has free capabilities, it processes those commands that you give it, send to the queue. So it could also happen that the command processing overlaps, like in this example here. We've sent 3 commands to the queue, and they are all processed in parallel by our GPU, because it has that many cores, so that it can process all of them in parallel. And maybe I should return once more. An interesting thing to notice here, the commands we send to the queue, they start being processed in the order of submission, but command 3 was processed the fastest, while the others were still in process. So that could happen, because always keep in mind, when you're using a GPU, it's a massively parallel processor. Okay. So how do we specify which queues we want to be created? For that, we use another configuration structure. In this case, vk device queue create info, and we pass that to the logical device creation configuration struct, which we will talk about in a minute. One important thing to note here, a queue always belongs to a queue family. So queues are organized in queue families, and the queue family is more important to keep track of, so to say. Queue families, different queue families can support different operations. So you might have heard of the async compute queue, maybe. So which is specialized for compute operations. There's also or there can be, depending on your device, there can be a transfer queue, which is specialized for transfer operations. So transfer operations might be really fast with specialized transfer queues, and compute operations might be pretty fast with an async compute queue. So this is what different queue families are there for. And commands can be processed in parallel on different queues. So you can imagine like that using different queues, maybe of different queue families, you can increase the parallelism of your application. Okay. You can use tools like, for example, the Vulkan Hardware Capability Viewer to find out which queues your device supports, which queue families your device supports. Some devices only support one queue family, but in this case here, we see 3 different queue families. We see this queue family here, and then there are 2 more, namely this one and this one. Let's focus on the first one here. We can see in its flags that this is a queue family that supports all the operations. It supports graphics, compute, transfer, and also presentation. Here, the small tool. I hope you can see it. So during this tutorial, we will only look for that queue family, which can do everything. So we will not use different queue families. We will only use that one that can that provides all the functionality for simplicity. Yeah, as I just said, we are looking for the graphics bit because we're doing we're using graphics pipelines, and we want to support the result onto a surface. So we are looking for the surface support, the presentation support. And now let's move on to logical device creation. So most of your Vulkan API calls that you will be issuing will probably be to the handle of the logical device. So a logical device is an interface to a physical device, but as with the Vulkan instance, you can imagine this to be a configuration, a special configuration that you would like your physical device to be running in while you use your application. So also in this case, you can, for example, enable extensions and so on for a logical device. So then your physical device must run in that mode that supports the logical device that you have created as an interface to a physical device. Okay, so we've seen this screen before already with the queue create information. In this case, we are creating one queue of queue family index 0, and we pass that to the pointer members in the VK device create info configuration structure. Then we enable extensions for this logical device. So for example, we were looking for a queue family that supports presentation because we would like to present our rendered result to a screen. So our physical device also needs the swap chain extension so that we get front and back buffers to render into and to present images. And finally, we pass this configuration structure to VK create device, which, if everything goes well, assigns a valid device handle through this output parameter to the VK device here, to the variable. Okay, let's move on to the last point here, the swap chain. So what is a swap chain? A swap chain provides images for us for rendering and presentation, for drawing and presentation. So at some point in our application, we will call acquire next image, which will then the swap chain will give us an image which we will use as our back buffer to render into. So we submit multiple draw calls, for example, and render into this current back buffer image. And when we are done with rendering, we call present, which hands that image back to the swap chain, where it becomes the current front buffer. And the current front buffer is then submitted or presented on your computer's monitor, like this. And in our application, we would like to render the next frame already. So we request another image from our swap chain through another call to acquire next image. So acquire next image gives us another image from those that the swap chain provides, which becomes our new back buffer. We draw into the back buffer. We present. When we are done, we again call present, which hands it back to the swap chain. And our application does not wait until the presentation is done, but it already acquires the next image from the swap chain already. So presentation and rendering can happen in parallel. Okay, so much for the swap chain. Just two more things that I would like to mention before we end this first lecture. Two important things, namely validation layers. I mentioned them during instance creation. So let's see what can happen if we do not use validation. Here we have a configuration structure for creating an image, and everything looks pretty nice. We have here image type 2D. We have set the S type, which should be the correct one, VK image create info, VK structure type image create info. Okay, seems good. The format, yeah, it's fine. Width and height is 512 by 512, one layer, one bitmap level, one sample. So looks okay, right? Does it? If we execute, or if we call this code, we do not even get an error, but there is something wrong, and we do not see it unless we enable validation layers. In this case, validation layers are enabled through a tool, and if you run the application again, we see a bunch of errors being printed to the console. So let's see what those say. One of them says we can create image if the image type that we specified is image type 2D. We must specify a depth, not only width and height, but we must set the depth to 1. We zero initialized the struct, so the depth was set to 0. And we wouldn't catch this error unless, or not that early, unless we turned on validation. So this is why one of the first things we will do during the tutorial coding session is we will enable validation layers. You saw in the small video clip, you can turn it on through a tool, but we will enable it in code. So we can enable it in code, and it will print those validation errors directly to the console. So always watch the console for validation errors. Because otherwise, image creation, in this case, seems to work, but it will fail because actually there are 0 bytes allocated for the image, because width times height times 0 depth. So yeah, at some point it will fail. Okay, and that error message can actually be found directly in the specification. So the Vulkan specification is very explicit in that regard, but it's also a lot to read. So, I mean, you can find it there, typically with the information given by the validation layer error messages. So the second point I would like to make here is the Vulkan specification is your friend. But so programming Vulkan means a lot of reading, but yeah, it has all the information. Yeah. All right, so we fixed this problem by adding depth equals 1, and problem solved. And with that, we have reached the end of this first lecture session, and we go on to the first coding session, which is 90 minutes. So we start talking about graphics pipelines, uniform buffers, and descriptors. So you didn't have to use them in part 1 already, but you're supposed to use them in part 2. So it's a bit less abstraction by the framework in part 2, and a bit more to do on your own from now on. Okay, let's start with graphics pipelines. Okay, this is a typical graphics pipeline that many of you will know how it looks like. So since many of you already know how to do graphics programming, but let's quickly go through all the fundamental stages of that. So we have draw processing. So this would mean one draw call, like for example, wiki command draw or wiki command draw index, as we will use in the tutorial code. Then next stage is vertex processing, where input geometry is processed, like our triangles, for example, that we're going to use. In that stage, we would like to transform triangles, maybe scale them, or position them with respect to some coordinate system. So also perspective division, so stuff like that. Then in that stage, we will want to use a vertex shader to do all of these transformations per vertex. Next step in such a graphics pipeline is the tessellation step. It is an optional step, so we can use it, but we don't have to. Basically, what it does is it subdivides our input geometry, in this case into just a subdivided triangle. So we get more geometry out of that if we use it. Next step is the primitive processing step. In that step, we can do work like duplicating the geometry through a geometry shader, for example, or not for example, through a geometry shader. Yeah, but again, geometry shader is optional, but we can duplicate the geometry, like for example, sending it to multiple views at the same time. We're not using that in the tutorial either, so but for completeness sake. So then next step is a very fundamental step in a graphics pipeline, which is the rasterizer step. So therefore, these graphics pipelines are often also called rasterization pipelines, because the rasterization is the fundamental step. There we move from a vector representation into a rasterized representation. In this case, our triangle gets rasterized. So depending on the orientation of our triangle, we get different pixels or fragments, more precisely said, in our output image, in our frame buffer image. So then we move on to the, so in this case, this is the final orientation of our triangle, let's say, and we move on to the fragment processing stage. In the fragment processing stage, we would maybe like to use a fragment shader to operate on each one of these fragments that have been set, or which are marked here in magenta color. We will use fragment shaders and so vertex shaders and fragment shaders in our tutorial code. So in this stage, the fragment shader. And finally, so the triangle has been shaded, so we set some different colors for all the fragments that were set. And finally, we have the pixel processing step, where not a lot happens, but in this case, actually, you can say that a lot happens. The image is being written into a target memory region. So this is the output step. So we can configure everything of that in Vulkan. And let's, for now, focus specifically on the usage of graphics pipelines and also the input that we will be using for such a draw call, like vk command draw. So when we create the graphics pipeline, we specify all kinds of parameters. So for the pipeline creation, we provide some convenience functionality in the framework, but so that you only have to pass a few parameters and also the path to vertex and fragment shader files. And you also have to specify which input buffers you're going to use for the draw call and which resources you are going to bind through the scriptors. And this is the fundamental differentiation here that I would like to point out. So the triangle that we saw initially, this is input directly to the vk command, so directly to the draw call. But there are also other resources which are bound through descriptors for our shader programs. We'll see in a minute. We'll see this a bit in more detail in a minute. So let's focus on uniform buffers for now. Uniform buffers are those which we would like to use for to contain our information for the shader programs, like for example a transformation matrix or a color value or other parameters. So how does this look like, or how does this work? We can see here the code of a GLSL vertex shader program, and these resources are always assigned to a certain binding specified through the layout binding ID. In this case, one uniform buffer containing color values and a color value and the transformation matrix. We can then use, for example, in the vertex shader, the transformation matrix to transform the input positions before writing them to GL position. We can also use that same uniform buffer in the fragment shader. Also here we see the same binding number and the same data definition. But in this case, we are using just the color value that we stored in the uniform buffer. Okay, so back to this overview here, so to say. How are those buffers bound differently to such a draw call? So the input geometry is, so to say, bound directly to a draw call. So when we record a draw call into a command buffer, then we bind the vertex input buffers, so to say, directly. So the following draw call uses them directly, but the resources that we are using in shader programs are not bound directly. We have to bind them through descriptors. So shader programs using descriptors. And the descriptor references then the buffer that this descriptor represents. Descriptors, we have to pay attention to use the correct type, in this case, type uniform, VK descriptor type uniform buffer, in order to represent such a buffer as we have seen in the shader code before. And this descriptor will then be provided to the vertex and fragment shader programs so that we can use it as we have seen in the source code before. Yeah, we are binding those descriptors before recording the draw call, and then the draw call has that. But important to mind the difference between those two. Yeah, and let's talk a bit more about descriptors. So we were here. Let's focus on descriptors. Actually, it is not entirely correct to bind descriptors, but we always bind descriptor sets. So a descriptor set is just a set of multiple descriptors. There's nothing wrong with only one descriptor in a descriptor set, but typically it's a group of associated descriptors. So in this case, we would have one sampler, one uniform buffer, and one sampled image descriptor in the same descriptor set. So these all have to have different binding numbers, so we can use them in shaders. So we can address the right resource in shaders. And a little bit more detail about command buffer recording now. So we haven't seen command buffers yet, except those calls to VKL get current or start recording commands, which abstracts command buffer internally. But we will we'll start to use them from now on. So we record everything actually into command buffers, and before recording commands like VK command draw, we can bind resources and also descriptor sets. I mean, we can bind vertex input buffers, for example, and also resources through descriptor sets. In this case, one descriptor set has been bound before recording the draw call, and for another draw call, maybe this one here, we record, let's assume we record that later into the command buffer, and before recording that second draw call, we would like to bind different descriptors maybe. So descriptor set B and descriptor set C in that example here on the slide. So this is the overall picture. And then we take this command buffer and submit it to a queue on the device in order for the commands being executed by our device. So the device unpacks the commands, schedules them for execution, and remembers which descriptors have been bound before recording every draw call or every command more generally. So the API or the driver or whatever remembers which draw calls, which descriptors have been bound before the first draw call. In this case, let's assume this is the one we saw with containing the sampler, the buffer, and the image. It provides those descriptors all to the draw call and starts executing it. And also for the second draw call, it remembers which descriptor sets have been bound before recording the second draw call, provides those to the second draw call, and the second draw call is executed on the device with the right resources bound. So this is the bird's eye view of the process. And yeah, here again, the full picture. Buffers are bound, provided to vertex shaders, and the vertex and fragment shaders are using the data in the uniform buffer while the triangles are rasterized. Okay, so much for the second part of this lecture. We now go into the coffee break, and afterwards, let's jump right into coding session of part 2.
So in part 2, we already used some vertex buffers to draw our geometry. And in part 3, we will use multiple of these vertex buffers. So this is what happened in part. This is what happened in part 2. We filled our buffer with the vertex data, like the positions of the triangles. And then we issued the command draw, the draw command, which then draw these triangles. So they went through the vertex shader to the fragment shader to your final image. This time, we will use 3 buffers for this, because we not only have positions, we also have normals and texture coordinates. For instance, normals are used for shading, and texture coordinates are used for wrapping an image onto a 3D object. This is the code from basically part 2 that we used for binding or for using one of these buffers. So it was like this for the bind command, where we had this array which contained one of these 3 buffers and also an offset array. And also an offset array, but in our case, we always start with 0. And we specified a 1 here because we only had 1 buffer. So the binding ID here in the struct refers to the position in this vertex buffer array. And the index starts with 0, therefore binding is 0 in this case. This time we will use 3 of these buffers. So also our array will contain 3 buffers, and the offsets also need to contain 3 zeros. And we need to specify that we will use 3 down at with the vk command bind function. And because we will use 3 buffers, we also need to specify 3 of these structs. So the first 3 basically the binding variable here refers again to the position in this vertex buffer struct. And we need to make sure that the vertex input attribute description also has the same binding. So we see this is for the first one, for the second one, and the same goes for the third one. Now we will take a closer look at the vertex input attribute description, because this struct is important for accessing these buffers in the shader. So as in the previous slide, the binding refers to the index in the array, and the location is now important because the location refers needs to be the same as in the shader, so that we can access the correct buffer. So for the position buffer, we specify 0 as the location, and also in the shader, we set it to 0. For the normal buffer, we now use location 2, so you don't mix it up with the binding. And we also specify in the shader with 2. And the same then for the third one, with location 1 this time, and also in the shader, we specify with location 1. We also need to set the format of the input. We specify the normals and the positions with vector 3, with 3 32-bit floats. And for the UV coordinates, we only need 2 32-bit floats. And the same goes in the shader. We use 3 floats for the position, 2 floats for the texture coordinates, and 3 floats for the normal. So that's most of it. That's for the vertex buffer parts. In the assignment, or in the coding part, we also will use an index buffer. So don't forget about that. It will contain the indices then. So now let's go to command buffer recordings. So in the rendering loop, we need to record commands to basically render our 3D object. And we can bind different descriptor sets. Like we've learned that descriptor sets contain the resources that we want to access in the shader. And we can, for instance, have 2 draw commands with each having individual descriptor sets. And once we have recorded this into a command buffer, we then send this to a queue, And once it is in the queue, the GPU tries to schedule it in a way that it finds best and executes them. So we put the command buffer into the queue. And then basically the command buffer is bind, the descriptor set is bind, and the draw call is executed. And then the second descriptor set is bound, and then the draw call is again executed. In code, this looks like it looks like this. We have our command buffer that we created, and we will use it to record these different commands. You can, like the prefix VK command specifies functions that can be, or that records commands into a command buffer. And all of these functions has as the first parameter a command buffer in which to record these commands. These functions are basically setup functions, or they configure the state that we want to use for renderings. And the last one is then the final draw command. So in this example, we first bind the descriptor set. We bind it to location 0. And we also need to have a pipeline layout for this. For instance, you could swap out these descriptor sets for all pipelines that use the same pipeline layout. Therefore, that is needed. Then we will bind our pipeline itself. We specify that it is a, oh, it's not highlighted, sorry. We specify that it is a graphics pipeline. And like you saw in the previous slides, we will also bind the vertex buffers. And we will bind 3 vertex buffers. We have 3 entries in each of these arrays, and we specify it with a 3 below. And then we will draw, or we execute the final draw command. And in this case, we will draw 1 instance of a triangle, and this triangle has 3 vertices, therefore 3 and 1.
Can I ask a question?
Yeah.
If you bind this vertex data, does the upload to happen when you call this bind vertex buffer? So does it happen?
There is no upload happening here. We have to do the uploads separately. I think we already did it in part 2, but it's a bit hidden. Normally, you would also like record commands that would, for instance, copy memory. I don't know if I should go into more detail in this regard, but yeah. Okay, and that's for the command buffer recordings. Now, multiple graphics pipelines. In the previous parts, we only used 1 single graphics pipeline. And for instance, it could look like this one, where basically all of the stages are used. But we could also create a pipeline that only uses some of the stages. For instance, tessellation is dropped here. And we have these 2 shaders, for instance, for vertex and fragment. And then we can have a third pipeline, which uses different shaders compared to the second one. And we cannot really hot swap, for instance, the shaders. We always need to create a separate pipeline for this. And that's not only about shaders, it's also about the stages that we use in the pipeline. And even more, it also depends on the settings that we use to build the pipeline. For instance, if we want to have one pipeline that draws filled triangles and one pipeline, and we also want to draw like lines, then we need to create 2 different pipelines, one for the filled triangles and one for the lines. And the same applies for culling. If we want to have backface culling or front face culling, we also need to create separate pipelines. And in this example, we have 1 pipeline created for filling, drawing triangles that are filled, and culling the backface. And this would look like this. And then we have a second pipeline that only draws lines and does not cull anything. And it would look like this. And this one we will do this in the part 3 then. And lastly, we have the depth test.
Question.
Yeah, sure.
You said we have to load the shaders individually for every step, or can the same shader be used for multiple of those steps?
You can reuse shaders. If you compile a shader, then you create a shader module, and these modules can be passed into multiple pipelines.
Okay. And is there something like precompiled shader options, or do we always have to compile it on the boot up?
There are shader caches built in, but you would need to code this yourself. Like if you have the GLSL code, then you compile this into SPIR-V, and you can save this SPIR-V somewhere on your disk, and then you can, for instance, if you encounter the same GLSL code again, you can, instead of compiling it, you can use this SPIR-V that you saved.
Oh, okay.
But you have to do this yourself. You can do this with a hash, for instance. You can hash the whole input text. And so now to the depth buffer. If you code like everything above the depth test, you will notice that the normals and the UVs can look a bit weird. And the reason for that is that we don't have a depth test yet. And so what is the depth test at all? In this example, this shows the use the rendering without a depth test. So we draw this pink triangle first, and then we draw this blue triangle, and it overrides all the pixels that it is overlaying. But it should look like this, that the red triangle is in front of the blue triangle. And in order to achieve this, we can use a separate image, which acts as a depth buffer, and it stores the distance basically from the camera to the shaded fragment. And we also need to specify that it is used, that we will use it for depth testing. And then we add it to the frame buffer. It will be part basically of the swap chain, and then it can be used to check if some triangle is in front or behind another triangle. And here it is again. Now with the depth test, we draw the red triangle, and now we draw the blue triangle. And now only the parts that should be visible are shaded with blue. So that's for the depth test. Again, the schedule, and have fun coding.
We are here, and we will have a 20-minute lecture, and then another coding session, and then another closing lecture, a short one. Okay, so now we will dive deep into Vulkan territory in this lecture, talking about command buffer allocation, memory, image layer transitions, and synchronization. So you already heard about command buffer recording, but we actually didn't allocate command buffers, which is also something that we must do if you would write everything from scratch. So yeah, a recap what we had before. We recorded commands into a command buffer, but this was abstracted away by the framework. So during the render loop, we recorded commands into the command buffer, then we send it to the queue, where the commands are unpacked and scheduled for execution, and then executed by the device. So by this queue abstraction mechanism, but still executed by your massively parallel GPU. So, but the open question is now how to allocate those command buffers, and so that we can record into them. Let's see. So this is what we already know. I mean, at least a part of that we already know, namely the part in the middle, command bind descriptor sets and command draw. But now we see also here the calls to begin command buffer and end command buffer. So between begin command buffer and end command buffer, we can record all those draw calls or other draws, calls. So everything that starts with VK command can be recorded into a command buffer. So this is the naming scheme in Vulkan. Yeah, here we have those two highlighted again on the slide. And within, we can bind descriptors, issue draw calls, and so on. So in order to get such a command buffer, we have to allocate one. And allocation happens again with one of these config structs where we specify that we would like to allocate a command buffer, in this case, from a command pool. So before we can allocate command buffers, we have to create a command pool. It cannot be easier because we're using Vulkan. So we start with with pool creation. There are certain flags for a pool, which we won't need during the tutorial, but I know there are flags for only short-lived command buffers, so we only use once, or some that we want to reuse, so the pool offers some flags for them. And also during command buffer allocation, there are flags for that purpose. But what is really important here, we have to specify which queue family we would like to send those command buffers to. So the queue family is really something that accompanies us from the beginning to many parts of the Vulkan API. So specify the queue family index here during command pool creation, and for different queue families, which we are not using in the tutorial, but for different queue families, we would need different command pools. Yeah, then again, the call to vk create command pool, which we also have to set the handle in the vk command buffer allocate structure. So you might know the drill by now. It's always the same. When we allocate the command buffer, we can decide if it is a primary or a secondary command buffer. The difference is primary command buffers can be sent directly to queues. Secondary command buffers are contained within other command buffers. We won't use them. We will only use primary command buffers. So just use those which we can send directly to a queue. In this case, we allocate one single command buffer with the call to vk allocate command buffers. Yeah, and when we have allocated the command buffers and recorded into them, like here on the bottom, so let's say we are done with command buffer recording, then we send it to a queue using the command vk_submit. So vk_submit takes a command buffer, or actually you can specify multiple command buffers, and hand them over to vk_submit, which then sends it to a device. And the correct term to refer to this thing that we sent to the queue for submission, for execution, is a batch. So multiple command buffers sent to a queue is a batch. It will be relevant later when we talk about synchronization. So just that you get the right term, a batch. We submit a batch to the queue. Okay, so much for command buffer allocation. Then let's quickly talk about memory. So this would be a main board. So and let's say you have a really big GPU in your main board, attached to your main board, and you also see here this should be your main memory, the RAM, random access memory. So let's see which different types of memory your GPU can access. So if you have a dedicated GPU, that GPU will have its own memory. So we call this memory the device local memory because it's local on the GPU, on the device. And the main memory of your computer, that is the host visible memory, because it's also visible on the host side, so on the CPU side. So that's host visible memory. And the GPU can access both types of memory, namely through PCI Express on a modern, typically modern computer. So the GPU can access different types of memory. The device local memory is referred to, or can be addressed using the vk memory property device local bit, and the host visible memory can be addressed with the flag vk memory property host visible bit. Yeah, so always those long names, but here we have device local, here we have host visible. So during this tutorial, we have always used host coherent memory, which is actually almost the same as host visible, So conceptually, it is the same, just no memory flush is needed when we write to host coherent bit. Yeah. If the host visible memory that we are using would not have this host coherent bit in addition, then we would have to manually flush the memory after writing into that memory. So it's but conceptually it's one and the same.
Question: Do we
yeah.
only have those types of memory available, or for example, the device local cache registers?
Device local cache? No, those we do not have. There is one type of memory which I didn't put on the slides here. There is some GPUs offer a type of memory which has both flags, so device local and host coherent. This is typically a smaller region, and I don't know exactly how it is implemented in hardware, but somehow accessed through PCI Express, so can also be accessed from the host side. But registers are not a type of memory that is addressed in this way. So.
And yeah. Just asking because on the OpenGL side, for example, if you clear some parts of the frame buffer before unbinding it, it reduces the amount of bytes written back to the device local memory and simply drops it already on the cache register side.
Yeah. Those are I think other details. So this is not a fundamentally different memory region that we are talking about here. So this is a slightly different topic, I would say. So if I got your question correctly, yeah. So the fundamentally different types are those two, on the host side in memory and locally on the device. And so in terms of Vulkan can address both of these memory types with the flags. So what did we do in the last assignments? We allocated a uniform buffer in host visible memory or host coherent memory, as the API, as the framework functions were named. So now just imagine for a moment what that means if we display a schematic view of our GPU here. So these boxes should represent the many cores of your GPU, and these are the level 2 and level 1 caches of your GPU. So whenever we access memory, that memory must be read into the level 2 cache of your GPU before it can be then further transferred into the level 1 caches and used by, sorry, that was a bit too quick, and used by the cores of your GPU for processing. So just keep that memory transfer in mind. And now imagine we moved the buffer into device local memory. Then you could maybe imagine that this memory transfer can happen a lot faster because it is already in device local memory when we need to transfer it into L2 and L1 caches. Okay, so now the question is, which type of memory which type of memory should we use for what? So for uniform buffer, is it a good idea to use device local or maybe host visible memory? So host visible memory is actually good for data that is updated frequently. If you update data every frame, then you have to transfer it through PCI Express anyways, once per frame. Then you can just put it in host visible memory because you only do the transfer once. So no point in, I don't know, moving it into host visible memory and then into device local memory because, yeah, you read it only once. And the slow part is through PCI Express. So a uniform buffer containing matrices would be perfectly well suited for the host visible type of memory. On the other hand, device local memory would be good for data that we write only once, or that we can keep on the GPU. So, for example, if you write to an image and we do not transfer it back to the host, then this can stay forever in device local memory. So, yeah, let's put it in an image, for example, would be best put into device local memory in most use cases. Okay, so during the assignment, or during part 4, we will add images to the rendering. So we will also transfer them into device local memory so that our rendering is as fast as it can be in terms of memory transfer. And speaking of images, let's quickly talk about image layout transitions. So this is something that you do not have to care about at all when you're using OpenGL, for example, but in Vulkan, it is just another aspect that we have to keep in mind. So just imagine what happens when we use an image. At some point, we have to load that image from the disk into main memory, let's say into a host visible buffer in main memory. And a common byte order for that image would be such a row-wise layout. So first row, second row, and so on. So just in terms of how the image is stored on the disk or in memory. And we can call this an image layout. And when we then copy over this image from a buffer into a VK image, in order to keep the data intact, this must be in the same layout. So the image must first be in the same layout as the buffer that we have loaded from disk. But Vulkan knows different image layouts. So it might be that a different image layout could lead to better performance. For example, reordering this data into such a C order curve, then it would maybe lead to better cache locality when sampling from such an image. This would be a different image layout. So when the data is being processed by a device, this could lead to faster performance. And in Vulkan, we have to care about such image layout transitions. So it's not optional, we have to, actually. Just one note here, so that you do not get the wrong impression from this talk. This is only a schematic view, so this is only an example. It could be that your GPU really stores the image in a C order layout, but it could also be that that it's just applying some kind of compression to the bytes or so. So image layout is opaque to the user. We do not know what exactly the image layout is. This is vendor specific. These are just examples, just as an illustration that these are different image layouts. So you do not specify the exact memory layout. You specify the usage scenario. So whenever you do some operations, you should, as a best practice, first transition is the correct word, transition that image into the appropriate layout for the operation. And you specify the usage scenarios based on the values provided by the Vulkan API, which can be, for example, undefined. Then there is a general layout for so a multi-purpose layout, but it's not optimal. And then there are all these optimal layouts here, like optimal for a color attachment, optimal for a depth stencil attachment, optimal for transfer source operation, and optimal for a transfer destination operation, which is copy from or copy to. So these are all different layouts, and your driver or your GPU, your hardware vendor, knows how to transform the image then so that it is optimal for each of these operations. And with that, we have to talk a bit about synchronization, because image layout transitions are very tightly connected to synchronization. Yeah?
Are each image layout device specific? So do you need to query which one you can actually perform?
They are device specific, but you do not have to query what you perform. You just transfer into transfer source optimal before doing a copy from that image.
Yeah, but the list of capabilities, is that something you need to query first from the device?
No,
which one
you just do the image layout transitions, and the GPU is free to do nothing. So I think on NVIDIA GPUs this happens. So I think NVIDIA GPUs just do not care about this, and it's a no-op. So they just do nothing. But AMD, so maybe this is a bit it's definitely a bit half knowledge from my side, but I think AMD at least performs some compression to the data, but not sure about that. So yeah, but you just do it, and the GPU is free to do nothing. Yeah. Okay. But the validation layers will tell you if you do not transform it, you did something wrong. Okay. Okay, let's talk about synchronization. we see here we're here back at the memory view and the command buffer view. And let's now record some commands into that command buffer. So we've recorded 4 commands into that command buffer, and now just imagine for a moment that, that those commands are accessing an image. So command 1, for example, writes to an image. Command 2 also writes to the image. Command 3 maybe reads and writes to and from that image. And command 4 reads from that image. And keep in mind, your GPU is a massively parallel processor, which can possibly operate or execute many of these commands in parallel. So it would be bad if those writes or the reads happened in parallel. So we, in some cases, we must ensure that the previous operation is done before we can continue with the next operation. So what do? We insert some traffic lights, like here on the slide, or let's call it by their name, barriers. So we would like to ensure that the command 2 cannot continue until command 1 has finished writing to that image, because maybe command 2 draws in addition some transparent stuff additionally to the image. So then the same between commands 2 and 3. Only after the barrier allows command 3 to access, it may execute. And same for the same barrier after command 3 and before command 4 may read the data from that image, because only then we can be sure that all the data has finished, all the writes have finished writing into the image. Okay, so let's say we have submitted everything to a queue. So remember, we call it a batch. And yeah, here the slide also calls it by their real names, pipeline barriers. And actually, in most cases, I would say, we do not only need pipeline barriers, but memory barriers. So this is just the term that is used in Vulkan. A memory barrier is a pipeline barrier. So pipeline barrier means the execution of subsequent commands are delayed or paused until the barrier allows them to access, plus memory access. So execution plus memory access must be synchronized. So this is then called a memory barrier, because the command could have finished execution before all the data writes have finished on the GPU.
Is there some kind of optimization available where, for example, a compute unit or so, which has done processing command 1, already allows command 2 to be executed on this part of the memory storage, despite not being completely done with command 1 on every other part?
So this is actually the power of Vulkan. You have multiple options here. You have the option to restrict a pipeline barrier to an image. Then only the access to that image is restricted, while other accesses to other resources can already happen. This would be one optimization. Another optimization would be you use multiple queues, because the commands within queues can be executed independently of each other. This is why we can use multiple queues to increase parallelism. So these are 2 options that you could use to increase parallelism.
My question was not for multiple resources, but for the same resource.
For the same resource? No. So
I mean, one texture, for example, Full HD or so, is executed on different compute units in parallel, but only part of it. Not everything is done at the exact same time, but the same image that is written is only done per compute unit, and then the next compute unit starts to do the unfinished part of the image.
Yes.
So is it possible that the second command queue can already access finished parts of command Q1?
Yes, I think you can specify for every image memory barrier the region. So maybe the layers, or I think even the regions within one image. So you can specify this in very fine detail. So yes. Okay. So moving on. So let's focus on this batch that we have submitted to a queue, and on this queue, there might be other commands as well. So there might be commands before that batch, and we could have also submitted further commands after this batch. So these are all on the queue, scheduled for execution. And we might want to know the exact point in time when that batch has finished execution, because maybe, yeah, we are waiting on the host side for an image upload to complete. Then we would like to know when this batch has finished execution. And for that, we can use a different synchronization primitive that Vulkan offers, which is called a fence. We will also use a fence during part 4. And the fence is exactly for that purpose. It is signaled when everything has completed executing within this batch. So we have an animation here. So command 1 has finished. The barrier allows command 2 to execute. Command 2 is getting executed. The barrier allows command 3 to execute. And command 3 is executed. Then the barrier allows command 4 to execute. And then after command 4 has finished execution, the fence is signaled, and we know that this whole batch has finished execution, and memory writes as well. And on the, oh, I think there's, my slides are stuck. Okay, let me start again from here. Okay. Okay, this does not work, then we will have to continue to this slide. So from the host side, we can wait on a fence signal to arrive. So this is the purpose of a fence, so to enable device-host synchronization. So whenever we wait on a fence, we are blocking the current call using VK wait for fences. So we are blocking the current thread using VK wait for fences. So as soon as we execute that command, the GPU, the CPU thread where this is issued is blocked, actively waiting for the fence signal to arrive. Then at some point the fence signal arrives and the wait is over for the CPU on that thread. So these were only two synchronization methods, fences and pipeline barriers. There are several more in Vulkan, which we are not going to cover today, but those two we will need during part 4. And once, let's go back to image layer transitions once more. And this is also the exact situation that we will encounter during part 4. Namely, we will have to transfer transition image layouts with pipeline barriers, or image memory barriers to be more precise, like this. So first we have an image in undefined layout. Then we transition it into a defined layout with an image memory barrier, which is a read and write operation, because it transitions the image layout of a given VK image in the middle of the barrier. You have to imagine, this is why the traffic lights are stuck in the middle. So here the image layout transition happens, like this. We transition it into the transfer destination optimal layout. Then the barrier finishes and allows the command buffer to image operation to read from the VK buffer and write into the VK image. And after that command is done, we have another image memory barrier, which is again a read and write operation. And again, in the middle of that image memory barrier, so right in the middle, the layout transition happens. And because we want to use that image as a read-only image during rendering, it is transitioned into the optimal layout for read-only operations, right there, and then the barrier finishes. So this is exactly the situation we are going to implement during part 4. And with that, we're at the end of this lecture, which took a bit longer than expected. So sorry for that, but yeah, less time for coding. So information before we close this. So what is there to pay attention to when we render multiple objects? So when rendering multiple objects, we have to pay attention to. So this is actually the very last task. So task 4.5 that not even the live coding guy did. But when we render multiple objects, the following can happen. So let's just assume this situation. So we are submitting a draw call. So for drawing object 1, so let's say we are drawing 3 objects in each frame, so 3 3D models. So this is the draw call for object 1 in frame 1. We submit it to the queue, and we also submit a draw call for drawing object 2 to the queue, and the same for object 3. And again, we are dealing with a massively parallel processor or chip. The GPU would process all of them in parallel. And since we are striving for high frame rates, we are not stopping there, but constantly sending draw calls every frame. So the host is sending draw call after draw call after draw call for object 1, 2, and 3 every frame. So here we see frames, the draw calls for frames 2. And now all the draw calls are submitted for frame 2. And the same for frame 3, as you can see in the part in the host area. So, and what we also do in our application is we are using a uniform buffer for storing the transformation matrix for each of those draw calls. So what we do on the host side is we write the correct data into the uniform data for the next draw call that we are going to submit. So, or let's keep it simple. Let's just talk about colors, but it's the same for transformation matrices. So in this case, we transfer the red color, which is suitable for object 1, into the uniform buffer. So submit the draw call for object 1 to the queue, and the uniform buffer contains the correct data for rendering object 1, the red data. So, and then, let's say our host is fast, we submit the draw call for object 2. But object 2 is a green object, so we write the green data into our uniform buffer, and which is the correct data for object 2. But let's see what happens now as we submit the draw call for object 2 to the queue. That data reads the correct data from uniform buffer, but drawing of object 1 hasn't finished yet. And now also object 1 uses the same buffer from our single uniform, the same data from our single uniform buffer for drawing. So it just switches right in the middle of being processed. And yet again, we submit the next draw call, write the blue data for object 3 into the uniform buffer. This data is only correct for object 3, but also all the other objects use the same data if they have not been processed entirely by our device. So how can we solve this? We can solve this, or we must solve this situation where we have so much parallelism by using a separate uniform buffer for every one of our draw calls, because we cannot solve it any other way. And this is what we have to do during task 4.5. We have to duplicate several objects, most importantly the uniform buffers, so that the rendering results are correct. Otherwise, we will see some artifacts during rendering. Maybe not on every GPU, maybe on some GPUs, maybe on others not, but yeah, this has to be expected. And this is the point of the very last task in part 4. And if they all get their separate uniform buffer, rendering will be correct. And this is it for our lectures. Now I have just some more further resources for you. So you might or might not know a paper of us, which is called The Road to Vulkan, Teaching Modern Low-Level APIs in Introductory Graphics Courses. It is actually the origin of this tutorial today, in a way, where we describe how we transitioned one of our university courses to Vulkan. You can get to my personal institute's page through that QR code, and there you will also get a link to that paper. And watch out for an extended edition of that paper, which is called Vulkan All the Way, Transitioning to a Modern Low-Level Graphics API in Academia. So we've got it accepted just last week. and the preprint is already available, but not yet online on my institute's page. So, but will be in the next I don't know, days or weeks. Yeah. All right. And you might or might not know our Vulkan lecture series on YouTube, which contains lectures in a similar style to those we had today. So, yeah. Okay. And with that, so you can find it on YouTube on the channel Computer Graphics at TU Wien, or through this QR code here. And with that, we have reached the end of today's tutorial. Thank you for participating in the name of all our team members. It's been a pleasure, and I hope, I don't know, you liked it a bit, at least. And you don't hate Vulkan too much now to ever use it again. So, thank you.